and maybe the surrounding. Anyway, it's great to be here. Hussein said that he asked me to give an overview for the whole meeting. He asked me to give the introductory talk, and I probably skipped that part of his email. So I'm not sure if I've satisfied him or not. I was going to give you an introduction to short pulses, tell you how to think about them, how to measure them, how they're made from lasers, and then just begin to make the jump into attosecond pulses. So I'm going to go from femtosecond to attosecond, and the next talk, I'll start talking much more about attosecond technology, as will others here. Okay, so that's what I want to do. Many of you may know all of these things. I don't know your backgrounds, so I thought I had to make a guess. And so I decided I would start out relatively elementary and work my way up. So a short pulse is just a constructive interference in time. I'm sure you all know that. I show it here by using, I think it's 7 frequencies separated by just a constant number, one after the other. Phased, as you can see, all of the waves are phased at the same place there. And you see the superposition written in red, and you can see what looks very much like about a cycle and a half pulse that we can make from a modern femtosecond laser. So it's just a constructive interference in time. Constructive interference occurs best when everything is phased together, and it occurs much less well outside when phases begin to be randomized, until, in this case, a recurrence occurs. A recurrence occurs because these are separated by a constant set. But in a good laser system, when we take a pulse out of it, they're continuous. So that's the short pulse. It's a constructive interference in time. I think, so I'm going to then introduce a way to look at short pulses and describe them, and I'm very much influenced, and I've taken some of the slides, from Rick Turbino's slides that are on the web. You may all know of them. If you don't, go look them up. He has a very nice course on ultra-fast optics, and you can see many things that are very useful. So Rick Turbino, he makes these slides readily available to everyone, and I've edited some, and of course I've thrown away many of them to bring this in line. So an ultra-short pulse has an intensity of phase versus time. So there you go, you can see the intensity, you can see the phase. You could think of the electric field as a field describing sort of the envelope or the maximum field, and e to the I omega t describing the phase aspect of it. It's a short pulse when the intensity is sharply peaked, and that makes it an ultra-short pulse. It's very convenient to separate off the average carrier frequency, e to the I omega t, and just take it outside, and be left then with the field as being the square root, or proportional to the square root of the intensity structure, called the envelope, and a phase structure, which is a correction to the e to the I omega t. This becomes the complex amplitude, and the complex amplitude of the pulse is generally what we're measuring and what we're interested in. So IT is the pulse, and IT, e to the I phase, is a function of t. Correcting the e to the I omega t that's assumed is a way to describe that. So if you want to measure the pulse, you've got to somehow get the intensity, and you've got to get that phase term. It's convenient to make the Fourier transform of that and describe it also in frequency space. So just the Fourier transform gives you the frequency version of this. And in frequency space, it has much the same structure. Here is what it was in time. Here is what it is in frequency space. You can see that there's a spectral amplitude and a phase, much like before. And just like we did in the time case, you can remove the e to the I carrier frequency, the natural frequency in the problem, and maybe suppress the negative frequency components, and you're left with an amplitude structure which is complex, containing the spectrum of the pulse and the phase, telling you the phase at which each spectral component comes into the amplitude. So this is equally a description of a short pulse. Frequency description or the time description. If you measure one or you measure the other, equally you know everything about it. So the spectrum and the spectral phase tell you everything about a short pulse. Now I'm going to leave this part, but I want to leave with the chirp, because chirp is such an important thing, and it's going to come up in attoseconds naturally, and I want you to understand, if you don't understand the chirp. Many of you will know this, and so to those I apologize. Going back to the time, I could do this also in frequency if one wanted, but going back to the time representation, think of an amplitude function or a whole function, which is an amplitude given by a Gaussian amplitude. There it is. And the phase being the carrier frequency, which I described before, as you can take out if you wish, and be left with the amplitude. And here is the piece that would be the phase in the complex amplitude, e to the I beta t squared. If you think about what beta t squared describes, it tells you the frequency, because beta t would be like a frequency. The frequency is the biggest of 0 plus a frequency beta that varies beta t plus an extra component, which varies in time, and it gives you a pulse that is chirped. You can see a representation of a chirped pulse there. It's a pulse whose frequency varies in time, and such a pulse is described in this way, a frequency chirp. If you take a pulse through a medium, a short pulse that's Fourier Transform limited, and it goes through a medium, as it goes through, the different frequency components travel at different velocities, the red exceeding the speed of the blue, and you end up with a chirped pulse as you propagate through. The red up here, the blue back here, and that's what naturally happens to a pulse as it propagates through an ordinary dispersive medium. Generally, ordinary dispersion, the red goes first, and so what I described is propagating through a regular dispersive medium. So the group velocity dispersion leads to a linear chirp like this, and group velocity dispersion is what I described to you in words as I walked across the stage. One last thing before I leave, because it's very important in everything to do with attosecond technology, but otherwise not so important in many other fields of optics. And that is, there is a constant phase in the problem. You might have thought, isn't it interesting we can take an envelope function, and we take an I to the mega t, and we haven't worried at all about the phase that goes along, just a constant phase of the I to the mega t. How do we know, how do we register the envelope function and the oscillation? And so that is known as the carrier envelope phase for obvious reasons. The envelope gives you a time, and the phase of the carrier relative to the envelope is the carrier envelope phase. So you can see why the term comes up, the carrier envelope phase. The carrier envelope phase is the same in the time or frequency domain. It's exactly the same number it doesn't make any difference. And it really describes what happens as you change the phase of the carrier relative to the envelope. Here you see an illustration in gray and black, so maybe it's not so easy to see, but this is opposite carrier envelope phases. We flip the phase, for example, by 180 degrees, and when this was pointing up, all of a sudden now it's pointing down because of this flip of the phase. The fields have flipped their direction, but it's not only a flip in the phase, you can change the phase any amount you wish. Here it's shown 0 phase, pi over 2 phase. And the pulse, if the pulse is short enough, really looks significantly different because of how the oscillation fits inside the envelope. Now, the last part of my talk, I'm going to talk about strong fields and attosecond technology, and many photons are going to be involved in the process, and this becomes extremely important in that part. I won't say so much about it, and if I look over the lecturers, I doubt there will be a lot said about the carrier envelope phase, but it is critical to every aspect, almost every aspect of attosecond technology. Okay, so that was a description of one way, or ways to look at short pulses. And you begin to know what has to be measured in order to characterize. Spectral phase and spectrum, or amplitude as a function of time, and the phase, the complex phase. These have to be measured if we wish to characterize attosecond pulses, femtosecond pulses, anything, whatever you wish. I thought the next thing I would do is go to this figure, which shows the duration of laser pulses starting right after the discovery of the lasers, only a few years afterwards, discovery of the lasers. And these are the shortest pulses that could be produced at the time, that's plotted along the horizontal axis down here. You can see that about 1964, actually I think the first mode locking was 1961, 1 year after the laser. And somebody put a modulator in the cavity and they could mode lock in some form. I think passive mode locking was discovered in 1964, and pulses shortened from then on. Then they were picoseconds, a few tenths of picoseconds, down to on the order of 10 femtoseconds over the subsequent 20 to 25 years. The process of making them shorter and shorter was largely a process of lasers interacting with nonlinear media, and this interaction, you could find a way to make it the interaction appropriate to the system, the laser, wishing to make a short pulse on its own. And so this process of improvement by orders of magnitude, almost a factor of 2 every year, was a process of learning to control dispersion and learning to control nonlinearities and how they interplay with laser cavities, and laser pulses or laser cavities. First laser cavities and eventually laser pulses. By 1986, we reached about 8 femtoseconds, maybe a little less. This is about a few cycles of visible light. It's about as far as you can go. Even now, we can only go down to approximately a single cycle of visible light. People are trying to synthesize half-cycle pulses, so-called, but they always have an underswing, so they're not truly half-cycle. You have to look at them the right way to think of them as half-cycle. And so it waited for about 15 years until we entered another phase of rapid decrease in pulse duration. So the first part came from nonlinear optics. Why was conventional nonlinear optics? Why is nonlinear optics so critical to this? Well, I have to get one frequency phased with the next frequency and the next, and somehow frequencies must speak to each other so they can organize their phase to be phased together. And nonlinear optics allows frequencies to speak to each other. And so it was critical to learn to play with nonlinear optics well. Equally for measurement, if you've got a short pulse and you want to know what it is, somehow you have to know what the phase of this frequency and this frequency and this frequency is, and so they somehow have to speak together. And so we need a nonlinear process intrinsically in order to measure this pulse. So it was really an issue of learning to deal with conventional nonlinear optics. I represent it here by a four-way mixing process, which is maybe the most critical of, but all number of nonlinear processes are used. And the development here was a different kind of nonlinear optics. You might call it extreme nonlinear optics, represented by different symbols. You can't think of it easily in photons absorbed and emitted. Maybe you can think of net photons absorbed and emitted. But it's much better to think of it in electrons being born by an ionization process, moving through the continuum, being pulled away, gaining energy, the energy being driven back to the ion from which it left, returning to its ground state, just like here, returning to its ground state, and giving out the energy it gained over this process in the process. You will find that this organizes the spectral phase, and we have to organize the spectral phase on our own with these kind of techniques. Okay, so now I'm going to go on and start to bring in nonlinear optics and then measurement, how it's done. Again, I will keep largely to visible lasers first. The first part here was nothing to do with visible. It's any short pulse. Okay, so the most important thing for us is nonlinear optics. I think you all are aware of Maxwell's equations and the nonlinear terms that, or linear and nonlinear terms that comes into Maxwell's equations. And by far the most critical that allows the laser pulses now to go down to a cycle or a cycle and a half is the term which is the Kerr nonlinearity. You can imagine why this must be. A number of photons are absorbed and an equal number are emitted. So we're all talking about frequencies all around the same thing, all the same frequency of the laser, in other words. And if you think about a laser, it has modes. And so it could be this mode and this mode minus this mode, and it fits another mode, right? It sits right on another mode. So we found a way, using this nonlinearity, the nonlinearity that involves frequency here, frequency here, frequency here, all of the modes of the laser, two emitted, one absorbed, and another one going to be, two absorbed, one emitted, another going to be emitted this way. And this is a mechanism to lock the phase. So I'm going to start out first with how to measure. It's also a mechanism to look at measurement. I'm going to start out with measurement, and then I'm going to talk about how they lock the phase. And I've got to keep an eye on time. I'll get that. Okay, so measurement is kind of easy to see in the autocorrelation way. So I'm going to start out with autocorrelation. A pulse, we'll have to assume it's been made in some way. A pulse is brought into a beam splitter. You create a replica pulse of the original pulse. In other words, you split it into two replicas. One going one direction, one going the other direction. The pulse going one direction is fed around through a delay line, which is controllable. The pulse going the other direction is brought in, and the two of these beams are combined in a nonlinear crystal. There's our nonlinearity coming in. A nonlinear crystal. If the two pulses happen to be simultaneously there, a photon from this beam going up and a photon from this beam coming down can arrive simultaneously, creating second harmonic, and conservation of momentum says it comes out in the bisecting direction. So we know where to look. If we look in the bisecting direction and we look for a blue photon created by sum of two reds in the bisecting direction, and if we have a material that does not store the energy, so by making a real transition, so a nonlinear crystal can be that, then we can ask, is there a photon from this beam and this beam simultaneously present? Delaying one arm relative to the other allows us to walk one pulse over the other and look at this degree of overlap. Here's an image of the overlap at this time delay. We have one pulse, another pulse, same time dependent, same pulse, except that it's delayed by tau. And then by moving the delay line back and forth, we can ask for the overlap and when the overlap goes away or when the overlap stays. This is called autocorrelation. It's called intensity autocorrelation. If you think about the field is given by a second harmonic generation term. So it's E1, E2. That's what it would be. But of course we're measuring the intensity, so we need to square that term. And when we square it, it looks like intensity times intensity. So this is a winter school workout. Assume that you have a Gaussian and work out what's the width of the Gaussian. You measure in this way by autocorrelation relative to the width of the Gaussian that you knew you put in your assumption. This is an easy problem to work out. I just do it because I want you to think about what is actually measured in this case. It isn't directly the pulse width, it turns out. So there are advantages and disadvantages, but qualitatively it's so easy to think about and to see this picture. Right? So this is a way of measuring the duration of a pulse, and it's used everywhere. Even more commonly used, and you probably have seen it in many papers, is a collinear or interferometric autocorrelation, exactly the same as I described to you before. A pulse comes in, is split at the beam splitter, making two replicas, one going in one path, one going in the other path. One of these paths is delayed as a translation stage to give you a variable delay. The beams are brought back together again at the beam splitter, where, well, they have to be combined, and since they were sent along the same paths and brought back again, this is like a Michelson interferometer, really. In some cases, radiation will go out this arm of the interferometer towards my detector out here. In some cases, the radiation will constructively interfere and go that way. So there will be an interference in each direction you see, and this is going to be what you measure out here, and you can see that interference in these oscillations in the interferometric autocorrelation. Of course, now you would say that there are advantages and disadvantages in this. If the beams are separated, each beam will come through a second harmonic crystal and create its own second harmonic. So there will always be a background. You can see it here. There's 0, there's 1. This is representing the background. One beam creating its own second harmonic, the second beam creating its own second harmonic, but not influencing the others any more than the others. As the delay line is changed, the beams start to overlap. The interference that we think about always is there. You start to see it. And so the interference turns on, and of course sometimes you have constructive interference and very strong doubling, and sometimes you have destructive interference and no doubling. And so, like before, you trace the superposition of the two beams, one over the other, but the interference gives you sort of this natural calibration. It just feels good to do it this way. It just seems so it's all automatically calibrated. It looks really good. In fact, it's no better than the other autocorrelation. It doesn't give you any better results. And there's a theorem, if you're interested in this, that says that a 1D measurement cannot be uniquely inverted to give you the pulse duration. Even though you might think that we've done nonlinearity, we've done many things correctly, and it seems qualitatively so nice that you cannot uniquely invert it. There's always some uncertainty remaining. And so that really drives us to a 2D measurement in order to make the full measurement of a short pulse. And this 2D measurement is not so much different with a lot of what is done in Attosecond technology, although the words are always very different.
So what is missing? What is the information that you don't recover from a 1D measurement?
Apparently there are multiple solutions that can give you the same autocorrelation trace. You've probably thought about it a lot.
Right. So you could say you want to know, if you discretize it into n frequencies, there are two n things you need to know. The amplitude and the phase.
So you miss
all those n, but you only make n measurements.
So you miss the phase.
So you can't, right, you could put in all sorts of different things. So when you go to 2D, you might think that's even worse. I've always thought that. But you get n squared things, n squared measurements.
Okay.
So now you unfold 2n things that you really want to know from the n squared things. And the tricky theorem is that actually works.
Yeah.
That, it seems like, that's as much of a mess as the other one, but it turns out that there's almost always a unique solution to that.
So these ideas are very close to the ideas of queer interfractive imaging used in queer interfractive imaging as well. And these are always 2D images looking at complementary structures. So it's the same theorem, the same set of ideas that drives them. So in short pulses, this idea led to, or at least is related to, I can't tell you led to because I've never asked for it to be known in this way, to a method of measurement which is called FROG, standing for Frequency Resolved Optical Gating. I won't spend a lot of time talking about FROG because I don't have that much time. In many ways, it looks just like autocorrelation. The beam again comes down, comes to a beam splitter where two versions of the same pulse are created. Two versions of the same pulse, one of which goes through a delay line, one of which does not go through the delay line. They're brought together in some nonlinear medium. It can be almost anything. But in most laboratories, it's a second harmonic crystal, just like autocorrelation was before. In this illustration, which I took from Rick Turbino, it's a Chi-3 material, and so any nonlinearity works, it turns out. The difference is instead of putting a detector out here, you put out a spectrograph, and you can look at the spectrum. If this were a second harmonic crystal, do everything exactly as before. A second harmonic crystal comes out here, and instead of having a single detector, you put a spectrograph, and you get a full spectrum of the radiation. This gives you 2D spectrum versus time, and so you now satisfy everything that's needed. And so inversion algorithms, which are not completely transparent, can always converge to, I can't describe them qualitatively that fast. They can always converge to a solution, as Ken said.
Yeah. What is the optical element before the last class?
You mean in this case?
Yeah.
This is done for a Chi-3 material, and the nonlinearity is a rotation of the polarization. And so this is a polarizer, and it's asking, how did we change by one pulse the polarization of the other? So it's a cross-phase modulation, like experiment. But this can easily be done, and almost all labs is done by second harmonic generation. So it looks very much like what I showed you earlier. I took it out of this because I think the very first way that Turbino did it was using a Chi-3 material and did the polarization. And this is the image he showed. What's the critical issue is to measure the spectrum. So you're measuring the intensity as a function of omega and T. So it's a 2D spectrum, and you can look at it that way. I put in one other figure to give you a qualitative sense in what's done. So this is again a figure of Turbino's, because Turbino, this is what he did. He did this frog measurement. What you're using is a gate, using one pulse to gate the other. And as you move one pulse, it doesn't have to be another pulse gating, it can be any gate, but you can use the gate, and as you move the gate through, what you allow to go through this gate is a different spectral component of the pulse. And so you're measuring something about the amplitude in this region and the frequency content in this region. And as you move over here, you're moving something about the amplitude and frequency content. And as you work your way through, that's always true. And even if it's one pulse measuring the other, even if it's two identical pulses, that's still what you're doing. You're bringing the pulse together, you're looking at what the overlap looks like in space, and in frequency, and in time. And that's enough information to recur. And what we do in Attosecond technology and streaking is exactly the same thing. I want to end this part by saying that autocorrelation or frog or any of these techniques is no different than almost all measurements that are done in ultrafast spectroscopy. In ultrafast spectroscopy, you bring some sort of pulse in, an excitation pulse. We bring it in and we excite a sample. Now a sample that we do not understand, we want to look at its frequency response. Before we had a nonlinear crystal here, something we do understand, and we always looking at its simple response, second harmonic generation. But here, we want to look at the temporal response of an unknown sample, and we come in and we excite with an excitation pulse. That excitation pulse might come from this pulse, directly down, or it might come from a different, but related pulse that can be made, and I won't try to describe how they're made in time. And then with some time-dependent delay, we come in and probe the sample, and we look at the response of the sample, for example, by transmission. The pulse could go up, transmission could go up, and fall as a function of time delay, and we watch the sample recover, and we begin to understand its time delay. Or it could be something else. We could have a detector out here and make electrons, and we could ask photoelectron probability. And many things could be measured out here with this basic arrangement of excitation, into an unknown sample and probing the unknown sample and detecting something as a result of radiation, phase changes, there are all kinds of things we do. But every experiment otherwise is the same. Okay, so now I've given you some idea how to measure a short pulse. In attoseconds, the details will be very different, but the concepts remain the same. We have to link the frequencies, we have to find a way. I want to end up this part, and then just for the last part of my talk, I want to make the jump towards the basic ideas in the strong field processes. So in order to make a short pulse, somehow we must lock the phases. So we need three things. We need many frequencies, a large bandwidth. We need a spectral bandwidth that's big. We need each phase or each frequency locked to the others, kept in phase with the others. And we must not only get them in phase, but as they propagate around in the cavity, we must keep them in phase. This is a modern femtosecond laser, which can go down to about a cycle or a few cycles if it's carefully designed. And it has very few elements in it. It has mirrors that are always essential for the laser. It has a gain medium. Ti-sapphire is frequently used because of its very large bandwidth, satisfying the many frequency criteria. It has a nonlinear element, although it's not obvious. The nonlinear element is actually Ti-sapphire itself. I'll explain to you in a minute. And it has a set of prisms along the pathway, and those prisms are there for dispersion compensation. And so I'll describe that to you as well. And these are the two critical elements in a modern laser. A nonlinear element, which is the material itself in many cases, and some method for phase or dispersion control, which in this case is two prisms. So let's deal with the issue of dispersion control first. We've already discussed this a little bit. If we have a very short pulse by hypothesis, and we bring it into a material, just low intensity, ordinary propagation through any material, every material has a refractive index as a function of frequency, except the vacuum. And so every material will disperse the pulse. The pulse that comes in, that could be transform limited, comes out with a chirp in it. You recognize that. We described it before, a chirped pulse. And in fact, the chirped pulse will look very much like this, with the red in the front and the blue in the back. For most materials, this is normal dispersion. So when you make an oscillator with two mirrors and you think of the frequencies that can sit there that will add together to give you the short pulse, a real oscillator has frequency-dependent mode spacing because the dispersion of the material makes the material effectively a different length for each frequency. It's exactly like a real molecule versus a harmonic oscillator. In a harmonic oscillator, the levels are separated by an equal spacing, each level one from another. In a real molecule, you have a non-harmonic potential, and the vibrational modes are separated by something that are not equally spaced. If you create a wave packet in the molecule, it only moves a couple of times until it disperses, and it's almost unrecognizable after a few oscillations. If you create a wave packet in an oscillator, a short pulse, if you don't do something, it will also spread out in phase and become unrecognizable over time. So in order to overcome this, we need some sort of dispersion compensation. So it turns out that the refractive index has two effects, of course. The refractive index, as we all know, creates light that separates in a prism. That's effectively the dispersion of the material, that the refractive index is different for each color. And of course it has the effect of giving us a chirped pulse as well. One in time and one in space. And so, although it took 20 years in order to discover this from the beginning of mode locking, and people worried about how to get around the problems of pulse dispersion, it turns out it's quite straightforward. You try to get dispersion in space to compensate for dispersion in time. Let me just show you how this works. Let's assume we have a short chirped pulse coming into the material. The different colors, when they come into a prism, are dispersed differently. The light goes through a different path, depending on its color. And when it comes up to a second prism, correspondingly positioned, as shown here, the light will compensate and go back parallel to itself. But you will find, if you come out here to a wavefront, and you trace the path length in space, and the path length through the material, the effective path length, you will find that the different colors have gone through different path length. And so you can have one color catch up to the other. In fact, it works very well, so you get normal dispersion, and by putting in a prism compensate pair, you can compensate for normal dispersion. The blue will catch up to the red. However, they're offset, as shown here. The blue now is offset to one side, the red to the other side. If you put a mirror and bounce it back on itself, it undoes itself in space, but the path lengths remain equally or doubly different. And so you can have now the blue catch up to the red without the spatial consequences that seem so devastating when you think of a prism in the first place. All beams, all colors are still going parallel. They're going parallel in the opposite direction. And depending now on how much material you put in, move this back and forth, this has normal dispersion and this has anomalous dispersion. You can compensate and make them balance, so normal and anomalous dispersion equal each other. And that's what's done in many modern femtosecond lasers. And that's the reason for the prisms. Now the second thing I want to talk about is how are the phases locked? How are the phases locked together? This is done by Kerr lens mode locking, the Chi-3, process, the nonlinear process I talked about in the first place. All frequencies approximately the same thing. But it's easy to see this qualitatively if you think about it. Imagine you have a low intensity pulse coming into a piece of material. Any piece of material is fine. In practice, it will be the Ti-sapphire crystal that will be the lasing material that is the nonlinear material as well. If it's low intensity light and the sides are parallel, it's just a block of glass or block of material, nothing happens to it. However, if it's high intensity light, the refractive index depends on the intensity in this form, n sub 0 and n2 I, where I is the intensity. And the intensity has a spatial property to it. The intensity is a Gaussian beam or something like a Gaussian beam in all cases. It doesn't go on forever. And so the light that propagates in this case will have its phase delayed because of this extra refractive index relative to what's out at the edges where the intensities are low. And so the beam will naturally be focused as it propagates through. This is like self-focusing. It's really the same idea as in self-focusing. In fact, its frequency content will also be increased. But it's sufficient here to think of only the spatial properties of it. So a real pulse, which has low intensity at the front, high intensity in the middle, and low intensity back here, goes through unaffected, unaffected, focused. Right? So that's what happens, and that happens inside the laser. Here's an illustration of that process. Here's the pulse coming in. It comes into the nonlinear crystal here, through a lens or through mirrors, but through a nonlinear crystals. The part that's best focused comes out, and you just set up the second lens, so that's the one that couples back into the cavity best. And all of the low intensity stuff doesn't couple nearly so well into the cavity. Now you favor, the cavity favors the high intensity part, or the part right in the center, and it suppresses the stuff out in the edges, the low intensity pulse. Squeezing on the pulse. Every round trip in this cavity, the pulse is squeezed shorter and shorter and shorter until it can be squeezed no more. And so that's what it looks like. That's a relatively modern femtosecond laser. It has almost no components, mirrors. These are just mirrors to concentrate on the nonlinear crystal, so just a set of 4 mirrors. Ti-sapphire material for lasing. The beam's set up optimally for self-phase modulation here, linking all frequencies in the cavity by this squeezing that I described to you before. And then its dispersion is controlled by a prism sequence. In some lasers, you will see the prism sequence removed, and you can put chirped mirrors in all places where you have mirrors to replace the prisms. Those are sometimes better because there's nothing to move, but sometimes they're worse because there's nothing to move. So it depends on your perspective. If you don't want to touch anything, get chirped mirrors. If you want to be able to optimize, then play with prisms. So there's the pulse I showed you before, and that's made by a system just like this. Okay, so now I've covered, I hope, how you describe short pulses, the technology for measurement, and the technology for making them. I won't talk about amplification. That's also important, but this would be only lasers then. I want to use the last. I have about 10 minutes left. My last 10 minutes to make the jump towards the physics of Attosecond. So the next thing is the other kind of nonlinear optics, extreme nonlinear optics. That's what allowed this jump in pulse duration, this changing in the slope, and allows the advances that have taken us to Attosecond. To me, in some ways, this all starts out 50 years ago. 50 years ago, Keldysh, writing in the Soviet literature in 1964, so it was 1964, wrote a paper which he called Ionization in the Field of a Strong Electromagnetic Wave. In this paper, he described placing an atom or a solid. He did both. They were simultaneously treated inside. In the case of a solid, you can think about a band-to-band transition. In the case of an atom, you think of ionization. So ionization is what was termed by the deals with solids as well. And in this paper, he said, if I were to think about using infrared, strong electromagnetic infrared pulses, long wavelength, well, he actually does with many pulses, with many frequencies, but infrared is the most interesting here. If I think about interacting with infrared pulses, if I satisfy the criteria shown here, gamma squared, where this is now called the Keldysh parameter for him, where gamma squared is given by IP, IP being the ionization potential, or the band gap, whichever you wish, over 2UP, where UP is the energy of an electron oscillating in an electromagnetic wave, just a free electron, otherwise at rest, just oscillating back and forth. And this is the average energy of this, called the Ponder motive energy. So over 2UP, if this is satisfied, then you can think about the removal of the electron from the atom as tunneling. So this is an amazing idea. It's obviously not tunneling. Tunneling is a DC effect. You place an atom in a field, and everybody studied it in the 1930s. People discovered that you could tunnel electrons from atoms below their barrier, and the electron just appears in the continuum. So he said exactly the same mathematics applies. You can think about this almost as if the field were static, even though the laser field can be quite high frequency and still satisfy this condition. To give you some idea, UP is the classical motion of electron. It's about 6 eV for 800 nanometer light and an intensity of 10 to the 14 watts per square centimeter. You can scale everything else from there because there's the formula. And if you want to think about it solid, if you want to think UP is 2.3 EVs for 3 micron light and for 2 times 10 to the 12 watts per square centimeter, and I almost certainly thought of that as a free electron mass. that is a fraction of the free electron real mass. I think, maybe I'm not. I have to work that out and check. You might want to check it. In solids, the electron or the effective mass is much lower. And I may or may not have put this in. This has been a highly influential paper. To me, it's really important because it's just amazing. He made this statement that an electron tunneling out of the system and into the continuum is this beautiful process. It looks like a beam splitter, if you will. It's amazing that a static field theory describes something that happens in the time scale of the laser pulse changing the field, and the window open for tunneling inside, say, an 800 nanometer laser pulse can easily be only around a few hundred attoseconds. So amazing again that a static field could, a static theory could describe this. So, thus in 1964 made the first step towards attosecond science, I think. And even hidden inside his paper is the second step. He never commented on it. I don't know how much he thought about it. And the second step was to say, what happens to the electron after it's created? I won't go through these equations. They're relatively straightforward. They're just F equals ma. If you think about the field, the laser field, E as cosine omega t field, and we think about the electron as tunneling out, being created by tunneling out. Let's imagine it tunnels out at some time, and we can associate the time. Then we can solve F equals ma, and we can calculate the characteristics of the electron born at any given time as a result. And this is such a calculation. And you find out the velocity of the electron as a function of time is equal to an oscillating term, electron oscillating in the field, plus a term that depends on its time of ionization, its time of birth. That's T prime in here. This is the beginnings of the ideas of a trajectory. An electron comes out. If the electron comes out, you can follow what it did. It was born at time T prime, all its characteristics by classical physics. So I just told you how to do that. I didn't go through the calculation because I don't think you need to see F equals ma, nor do I have the time to do it. But just to make it clear, the electron is born somewhere. There it is. V equals 0, T equals some time. Calculate from then on for all different phases of birth what is the characteristic. And you'll find out an awful lot about what we will see in attosecond science. Actually, if you do that, do the same thing for circularly polarized light. An atom, Coulomb potential in a field, the electron is born at some time, the field pointing in some direction. Calculate what happens to that electron in circularly polarized light. Change the phase, look at all possible phases. You'll see it's extremely different, linear versus circular. Very different behavior, very different results of the calculation. And when you're done, you will understand a lot about trajectories, and you will understand the essence of the Attosecond clock that many people talk about. So anybody wants to know about the Attosecond clock, I wasn't going to talk about it, and I doubt anybody else here will. Come and find me, and well, work this out. This is all kind of interesting to do. It's freshman physics. It won't take you very long, and it'll give you a feeling in your fingers for an awful lot of Attosecond science. Okay, so what Kaldis didn't understand, what he didn't recognize, is the next step. So here is this classical-like view of an atom. I told you that a moment of birth maps by F equals ma to a trajectory of the electrons. You can calculate what time or under what circumstances that the electron might be driven back and collide with the ion from which it went. Let me just make it clear that it could easily happen. The field is pointing, say, that direction, or force on the electron is that direction, I don't have to worry about the charge. The electron is pulled away, the field changes its direction, the electron is driven back, collides, recombines. Okay? It turns out that for fields more or less anytime after the peak of the field and for the next quarter of the cycle will be driven away and has a chance to come back and collide, and when it comes back and collides, it can recombine. It turns out that for an electron born late in the field, it will come back earlier with low energy, recombining, giving out its energy as a low frequency photon. If it's born a little earlier, it comes back, giving out more energy as a higher frequency photon. And finally, there's an optimum time of birth in which it comes back and gives out the highest frequency photon in the problem. And that gives you this is the essence of the Attosecond pulse. Okay, so first thing you see a large bandwidth given by F equals ma. You see a chirp on the pulse, just like we described before. It's a red chirp, or it's a blue chirp, right? It's going from red to blue. You'll see if you do F equals ma that the frequency of the electron coming back depends on the wavelength of the light that's driving this, the ionization potential of the atom, and then we need the tunneling. Depends on the field at which the electron is born and things like that. But this can easily go up to a kilovolt. Not easily, but it can go to a kilovolt under some circumstances. And so the bandwidth can be huge, and it's frequency coded or chirped pulse, just like we described before. Okay, so just to make sure that, yes, please.
How do I see that with many atoms, this process will give you a coherent light?
Yeah. So I was going to do that. Can I wait just 2 or 3 slides? I'll just comment it. But I'll spend some time on it as much as you wish. But if you don't mind, 2 or 3 slides later. I know you all study quantum mechanics, so I can't just leave classical physics in the nano. And I'm almost done. I know I'm almost done. So I want to make sure right away that you make the transition from classical physics and from classical trajectories to quantum trajectories. So here is a quantum mechanical illustration, like a quantum mechanical picture, if you wish, of how that process works. You have an electron, bound electron, now a wave function. The electron splits, creating an electron left in the ground state, plus an electron wave packet in the continuum. That tunneling is fine. Cavity's dealt with tunneling. That's a quantum mechanical effect intrinsically. The electron, of course, is phase related because it tunnels from the ground state out to the continuum. The wave packet propagates. That I really need a movie to show, so I'll have to illustrate it. And some portions of that wave packet, the wave packet gets pulled apart and changed. And some portions of that wave packet are driven back to overlap the wave function from which it left, creating finally an interference or a dipole in the atom as this interference coming back. So a quantum perspective is a bit like an interferometer, an electron being driven out, driven back again. Classical physics gives you the trajectories. You can make it semi-classical physics and get the electron phase along the trajectories. And the sum of all trajectories, all moments of birth, give you the wave packet that I've described to you in quantum mechanical language. So this is a wave packet, which is a bit like a shear interferometer.
So which fraction of the electron gets handled typically?
Excuse me?
Which fraction of the electron gets handled in typical experiments?
Generally, we don't tunnel, you need something back here, right? There's no,
Right.
It's clear, you need something back here. You can't go back to an empty state.
Right.
This is like any nonlinear process. You go back to the state from which you left, and you left lots of population. 10%, 5%, something like that, small portions. Depends on the experiment.
Right.
But you don't generally do too much. Okay, so I just wanted to do the last thing. I just want to give you a qualitative picture for this interference or this final step. And so you understand the whole ideas of the coherence. So this is taking and isolating that overlap. Let me just make sure you understand what I'm talking about. Here is the overlap between the wave function and the wave packet. I'm only going to concentrate on that part. The wave packet is going to go across this thing, and it's going to do its, and it's going to, I'm just going to take a moment in that interference. There it is. And now I've got it coming back again, and you can see the superposition. I just want to the wave function functions, in this case, a Gaussian plus a recollision plane wave. And there's the sum of the two here, and there's the sum of the two, and well, that's the sum of the two. This is the square to give you the probability, and that's the dipole, therefore induced. And as the wave packet moves, in this case going in this direction, the interference changes. The square is there, the dipole is there, and so you can see the dipole oscillation. The dipole first was there, now it's here. As the interference evolves, it moves back and forth. An oscillating dipole emits radiation. The radiation that's emitted is the radiation that you see. This is the attosecond or high harmonic pulse, the XUV radiation. That's interesting. This is the dipole, the strength of the dipole that's induced in a plane wave approximation. And the dipole that's induced is the transition moment, or essentially the transition moment. So the electron recombines or induces a dipole two ways to see it. So you can see that the radiation that's created, that's going to become this attosecond pulse, the radiation that's created has an amplitude and phase given by the amplitude and phase of the recollision electron as translated through the transition moment of the atom as it goes back down to the ground state. Okay. I want to make, as I end up this part, and I'm going to almost end and only go a couple more, and I'm coming back to your point, I think, the next one. A couple of things just to make this now practical. The pulse I showed you in the first was only one cycle. You can't make a one-cycle pulse that stops anywhere like I did. You need some real pulse. Mostly in many laboratories we have a multi-cycle pulse. This is not realistic either, but you can imagine the pulse. What happens in that case? The wave function, a piece of it ionizes, creating a wave packet, comes back, recombines, giving you an attosecond pulse. This happens the next time and the next time because the wave function can be multiply divided. So we create a train of attosecond pulses, one, followed by another, followed by another, followed by another, each separated by half a period of the laser light, a frequency, a set of pulses, one after the other, separated by half a period is a set of frequencies. And so if you look at that in the spectrograph, this is a set of frequencies. These are called the high harmonics of the laser light, and the harmonic number can go in many experiments from 1 eV approximately to 100 eV, so 100 harmonics, and in experiments done in the infrared, you probably hear about from Margaret Renee tomorrow, you can go down up to 3,000, I think it is 3,000 harmonics. Infrared driver going to kilovolt. So this is the process of high harmonic generation. Attosecond pulses, almost the same thing. Okay, so now I come back to what I'm going to say. So of course, I've talked about one atom. And I've talked about a laser beam coming in, so let's make it realistic. Here's a real setup. Lasers out here, all complexity is in the laser. If you want to make an attosecond pulse, you've got to do something to the laser. The beam is focused into a jet of atoms, or a cell of atoms, or a fiber of atoms, or molecules, or in fact even solids it can be in some circumstances. The jets that we use are supersonic jets because we do a lot of work with molecules, supersonic jets. The beam is expanded into the vacuum. It's approximately 10 to the 18, maybe 10 to the 19 atoms per square centimeter, cubic centimeter. The length of the jets are in the order of a fraction of a millimeter. So that's the number of atoms that we're dealing with. But other people, you'll hear here, use cells, which can be longer. They can be fibers. It's basically a cell or fiber. It's like a cell. So there are different ways you can do this. These are not just a single atom process. So now, why does every atom work? As you go along, the laser beam sees one atom randomly positioned. It ionizes, electron comes back, makes a wave packet, and now the wave packet and the light propagate along exactly together. They find another atom, the next atom ionizes, electron comes back, recollides, creating a wave packet which is identical to the first, as long as the first propagated with C, phase matching again, propagated with C along with the fundamental. Nothing about the atom remains. We took the electron from a wave packet, from the wave function, and we returned the electron back to the same state from which it came. Nothing with the atom remains. Only the light comes out. We don't know if it stayed there. We don't know if it went out. In other words, until a high frequency light starts to move out of phase, created there, with the high frequency light created here. So phase matching light in any ordinary nonlinear process works here as well. It's more difficult here because the frequency differences are much greater. Effectively, X-ray is nothing, and it's not true for visible light, of course, which is highly sensitive to electrons and especially ionization.
So it's not bosonic enhancement. It's not bosonic enhancement in this case. It's like it's coherence in time.
This is just coherence, just like in ordinary harmonic, I should say. It's really very similar to second harmonic. But it's not a single atom process. You can understand so much of a single atom that it's easy not to say. I'm not sure if I'll go through all the talk without saying this. And everybody in the audience would say, well, who would care? I got an attosecond pulse from one single atom. What's the chance of it? There's no interest. It becomes interesting because I can have a macroscopic number of atoms doing exactly the same thing and giving me that. So conversion efficiency, maybe this is important to say. Conversion efficiencies in the region of 100 eV, 50 to 100 eV, in things like argon, can be pushed to about 10 to the minus 5. That is fundamental. It's not bad. It's not great, but it's not bad. If you go more extreme, if you go to high harmonics and go to a kilovolt, I think the numbers are not clear yet, but it's not as good. It's clear. And there's a lot of work trying to optimize this. So in the region of 50 to 100 eV, you're propagating along, the XUV is propagating along, but you think about 100 eV photon is ionizing argon atoms around, or even argon ions is ionizing and being absorbed. And so eventually you get to a point where the absorption of this radiation is equivalent to what's being added. And that's the best you can do. Your absorption limited, and that is about 10 to the minus 5 conversion efficiency in that region in argon. And we can reach that in argon in some systems. We cannot reach that in helium along with like that. And whether we will be able to or not is not clear. Okay, this is I think my last, or second to the last slide, and I think I definitely have to be done. So the next part is how do you get an attosecond pulse? It's more specialized. I leave that for the next, my next lecture, which is tomorrow, I think, at times. There are a number of gating techniques. I won't describe them here. There are 5 of them listed here, and I'll start out, not exactly here, but not very far from here. And I'll tell you, I'll pick one and show you how it works, and how we create a real attosecond pulse, and then how we measure. So next lecture, making, measuring, controlling attosecond pulse. Thank you.
Thank you. Here you go. You have your first assignment, right? Calculating classical trajectories for these electrons as they come out in a linear or a circular pulse, right?
And the autocorrelation.
And autocorrelation function. And Paul would like to see the results this evening.
That's a good idea. I didn't think about that. That's a good idea.
So,
questions? Hopefully not everybody gives you assignments because you have a lot of things to do this afternoon.
that's
They
right.
do. Any
Questions?
questions? Questions, please.
When we do frog and we find that the configuration, is that completely unique?
Yes, I'm not an expert who says this. I have read the experts who do say this, yes. You can you can show a theorem that the solutions that, Only a set of measure zero. So there is a unique or essentially unique solution. Yes, there is a unique solution.
You described something of the thought in the harmonic generation variation in your case with the model slide. So can you explain that one more time?
I can't, but I didn't quite understand every aspect of your question. Could you please repeat? Then I will try. Then I will try it.
So you, so in your three-step model slide, you mentioned how there is a from net to radius, and you mentioned something.
Can I tell you why that is the case?
Yeah.
Yes. I will tell you, and I will point you out to go back and work it out. So let me do that. That's not back very far, so go back.
There is a white ball, if you need a white ball.
That might, I don't know if that's easier or not. Let me try to do it with my hands, and I can go to the whiteboard if it's useful. When you do classical trajectories tonight, and you release an electron at all possible phases of the pulse, you will find first that if you do it simply, turn off the Coulomb potential after the electron goes, so to keep it simple. So let the electron propagate after it's released, just in vacuum. Then you'll find that anytime after the peak of the field and before the zero crossing will allow recollision. In fact, you'll find that the electron will go out and come back and cross its initial position. You will also find that there are two ways or two times when an electron can go back with the same energy. You can see this actually in your mind. Let's imagine an electron born at the peak of the field. It's pulled away from the quarter cycle. Its momentum carries it the next quarter of the cycle against the field. It's driven back for a quarter of a cycle, gaining energy again. And its momentum carries it to the ion just as the field reaches its peak and it goes back. So it collides with zero velocity if it's born here. So now in between it'll go up. You can trust me. Let's think about the one right here at 90 degrees. It barely gets away before the field changes direction and gets pulled back again. There's no time to pick up energy, so it collides with zero velocity. So the curve is like this. So the electrons born here will return back more energy, more energy, more energy. They reach a peak, which comes at the zero crossing here approximately, and then they turn off again. It turns out that experimentally we can choose to look at these ones, the ones born late, and almost everybody does. And so you get ones born late and colliding early, and they collide with lower energy, working their way up the curve. Born a little earlier, colliding a little late with more energy. Born by being born even a little earlier still and colliding at the optimum time. And this gives you a time frequency mapping of what you would see in the experiment. And that's exactly what you see. Is that clear? Good. Yes?
Okay, how far can we go to then the time delay of these two pulses?
How can you make two?
How far can we how far can we go to the time delay? How short can the time delay be?
I think you're thinking about pump probe that I described earlier. Invisible.
Yes.
In that case, I can bring them right superimposed. If you're thinking about back here where I talked about, you can do spectroscopy. There's no reason why that can't go right down essentially to zero. The two pulses could overlap if they wish. Now, maybe it's not easy to understand when the two pulses are superimposed what you're seeing. Maybe it is, but maybe it isn't. We can make pulses, individual pulses, with these new attosecond techniques, now to 65 attoseconds. And so, in principle, the time delay could go down to, without pulses overlapping, to about 65 attoseconds. Just an attosecond to make sure everybody knows it. I'm sure you would do, but it's 10 to the minus 18 seconds. So you can go to 65 times 10 to the minus 18 seconds. I mean, in principle, in practice, it's pump probe is kind of difficult yet. And you have a second.
But how do they make this happen? I mean,
I showed
the time delay, you have to tune the distance for the
Yes.
pathway, but for the distance, you have this speed of light, which is equal
That's
to
exactly
the speed.
So it's easiest to see in one of these, like autocorrelation. Let's go back here to this one.
Yes.
So let's go back. I could have kept everything in this. This would have been good maybe. So you take the pulse. So now the pulse, you divide it in two by taking it through a material and reflecting it off the material. If the pulse is very short, this gives dispersion problems. And so you need to correct this one as well. But that's a detail. Let's assume that the pulse is a true identical pulse after this. So now I go through a delay line, speed of light, we know. And so if I need a little more time delay, I just add a little bit of length. And the lengths are kind of convenient. You travel a micrometer, right? A micron is the period of visible light. It's a couple of femtoseconds, right? So a micron is a couple of femtoseconds. So if I move a micron, I make a couple of femtosecond change. And so I can manipulate these pulses to overlap with the time accuracy. I can easily go submicron. So there's no reason why you can't do this very, very, very accurately on the time scale. Even on Attosecond time scales, you can do this very accurately. You can also find ways to do this which are common pathways where you don't even have to worry about fluctuations. In a real experiment, you've got some mirror, and this mirror might move a little bit, and you can easily get a micron error. To get around that in a real experiment, you could feed back by using interferometers and try to correct this. Or you can try to find ways to do it where everything uses the same path. And there are ways to do that. I can talk to you afterwards about that.
It just occurred to me, in these beam splits, are you splitting the fields or the intensity?
Well, you think about it as splitting the intensity, I guess, but is there a difference? We buy a beam splitter, it's 50-50 beam splitter, we think of the intensity, or a 30% beam splitter. I guess I'm not sure I understand.
No,
There would be a field version of that number, I guess, but I think intensity. I say intensity. So these are very convenient experiments to do because the delays are just appropriate. What is not obvious, I didn't make obvious, and that is, what if you want to change the pulse, the pump pulse frequency? I applied it in the other one. Turns out you can make continuum in between here, so you can change the color of this light without changing its time duration, almost anywhere you wish. But that's femtosecond technology, and you can choose to go that way. And I doubt any of the speakers will. But if you want to know about it, anybody wants to come and ask about how visible near the vertical is done, I can describe a lot of it to you if you wish.
And I think you should, but before we sort of break for a few minutes, in order to stretch, I really need to stretch. And Ken sets up. I'd like to ask one question. I was intrigued by this thing you brought up about this few mini atom effect. I think it was the phase batching issue that you brought up. So is this picture more closely related to a classical picture where each atom is an emitter and you do like a super radiance? You take the collective behavior of the atoms into account? Or should I look at it as a mini atom wave function picture? Which one is it? In order to be able to simulate.
I think of these atoms as randomly oriented. So I can't think of it. I think of
So
many atom
it would
picture.
be more of a classical picture as it's
more
individual
classical
images.
Individual atom. What's
Influencing
what's good about harmonic generation, these nonlinearities in general, is the characteristic of the atom disappears because you go back to the same position. So I don't care where the atom is. Everything is organized by the light, and the details of the atom are moved. If the atom changes, or if it's a molecule, if people do these experiments, if you excite a molecule, and let's say the nuclei just begin to move a little bit, now information is somewhere else. The phase is gone, and you've lost that contribution. And people do these experiments. You can watch the atoms move in a molecule just a little bit. They only have to move enough so that the wave function no longer overlaps the original wave function when you've lost harmonic convergence.
I have a follow-up question. So tunneling is a quantum effect, so,
Yes.
so there is fluctuations associated with your electrons.
Excuse me, is
Tunneling is a quantum effect,
Yes.
so we imagine the fluctuations in the tunneling terms. Does it give the line width to your system, the additional line width? Or is your pulse so short that it's kind of a...
Yeah, the issues of the characteristics of the electron wave packet that are created in the longitudinal direction, in the direction in which it comes, are difficult to deal with. It's hard to get a hold of them experimentally. I don't think there's a clear experimental measurement. People worry about it theoretically, and there's all kinds of people that think about it. First, there's issues of tunneling time, and is it meaningful? So there's a great deal of research done on tunneling time. I mentioned the Atto clock. One of the ways to do it is the Atto clock. So let me just describe it to you under this context. So we have a molecule or an atom that wishes to tunnel. And you will find if you do the classical physics in circularly polarized light, if the field is pointing in this direction, the electron will go in that direction. You just work with the classical physics and you'll find. And so if it goes in that direction, you sort of knew something about what direction it was in tunneling. And if you know the time, the field going around, you know the time. So you're starting to get time information, this direction in time, you know, the way direction the field is pointing. And so can you then put somehow information in here that looks at it? You could take a molecule where you know it should tunnel in this direction. Is it delayed? Or you could take an elliptically polarized light that tries to bias the tunnel in this direction. And is that bias a little bit off, for example? And these are argued to be related to tunneling time. And it's an interesting subject. I think personally, this is my own view now, I think in the single atom, a single electron, a hydrogen atom, there's no tunneling time, I think. Quantum mechanics is clear. That's my view. Maybe in a multi-electron system where there's more complex interactions and electrons just don't do what they're told to do right away. Maybe there is an interesting issue here. This is I don't work on it, so I only look at it from afar. That's my view. And so maybe you have a chance to look at interesting multi-electron.
No, I'm just curious because it's...
So,
But we're still, I mean, I'm confused, we're still talking about quantum mechanics. I mean, we're describing these atoms or molecules with a quantum mechanical perspective. So...
It's incredible that classical physics takes you as far as it goes. It's amazing. But yes, of course it's a quantum mechanical process. It's
But I
really
think we
an
cannot...
atom or molecule.
But, I mean, my point is that we cannot say that this, like, I don't understand the time that we describe here.
Well, in my view, I think you and I would agree. I think in a simple case, hydrogen atom, so I don't have to think of it too hard, there is no time. Electron always exists underneath the barrier, and so it just comes out. There is no time. It isn't there.
So what happens when you have, like, more complicated atoms and molecules?
Well, maybe this is my naivete about complex systems. I think of an electron trying to be removed from a complex atom is interplaying and interchanging with the electrons that are there. And so the electron removal can easily interchange. It can excite another electron in the way out. There's a whole set of things that are involved, I think, in removing an electron from a multi-electron. And so at least to me, I could imagine phase domains or things that look like atoms. And this would be a measurement then of this more complex environment. That's what I think. Now, I told you I don't work in this, so I'm not an expert. I'm just giving you my view. So if you've got good ideas in this, I'd be happy to talk to you about it, because it's an interesting subject. So it's not that I haven't thought about it some, but it's not my field of research.
So this looks like a good opportunity for those who would wish to come forward.
Yeah,
But we
great.
will break out for a few minutes. There is some stuff, yes, to drink or eat. And then we will come back in very few minutes. Okay? Thank you.
Thank you very much.